Assalamualaikum and very good day. I am Asrani Lit and I'm with the Department of Electricals and Electronic Engineering, University Malaysia Sarawak, UNIMAS. And the focus of my presentations is about evaluating NOC and WINO architectures for multi-core architecture performance. So this is the roadmap of my presentations, which basically consists of four main parts, and they are introductions, methodologies, result and analysis, and we'll end up with conclusions. Without further ado, first I would like to begin these presentations with introductions. The arrival of many cores, which have more than 100 cores in a single chip, is predicted by the recent advancements in computer architecture designs. The conventional on-chip networks in this context are not scalable in terms of latency or energy consumptions, which causes execution bottlenecks. And recently, wireless network on chip or WINOC has been considered as a potential solutions to the scalability concerns of the conventional multi-hop NOC architectures. The WINOC is a promising paradigm for the implementation of an on-chip interconnects that can support the modern many-core that demand a high level of parallelisms. On top of that, WINOC is the NOC architectures that integrate the wired and wireless interconnects to reduce the high latencies of the wired planar communications with an express long-range wireless channels. And the development of Winox as a potential complement to the traditional NOC has been motivated by the advancements in integrated receivers as well as the millimeter wave antennas. One of the key design elements that affect the overall system performance and its network cost is the architectural formation in NOC. For examples, the physical layout, the link between processors, the location of radio hubs, and the number of wireless channels adopted over the WINO networks all contributes to the WINO performance. These figures illustrate the general example of 8x8 or 64 cores mesh NOC architectures. Generic NOC architectures consist of heterogeneous intellectual property or IP cores, such as processing cores, graphic engines, video processors, embedded memory blocks, or I/O device. And each IP is attached with a local router or switch which connect a core to its neighboring nodes via NOC interconnections. Processing tiles is the term that we use to describe the basic processing units that execute particular application software, and the communication between tiles is performed by the data packet exchange that can operate by the network interface modules. This figure illustrates the general example of 8x8 or 64-core mesh WAN architectures with 4 radio hubs that are distributed evenly over the WAN architectures. The addition of radio transceivers to NOCs enable a single hop communication between the distant tiles that would need multiple hops in a traditional wired NOC network. The next presentation is on methodologies that has been carried out in this work. So this is the evaluation framework for these works. The evaluation of the investigated architectures is use cycle-accurate system C-based simulators, which is called NOCSIMs. As an input, the mesh WINOC configurations is defined in the YAML files. Then the NOCSIM WINOC simulators is employed as the runtime engines. Afterward, once the simulation is completed, the result and statistic can be obtained, which are in terms of the latencies, throughput, as well as and energy consumptions. This is the example of simulation outputs provided by Noxim simulators once simulation is completed. As can be observed, the result is statistic in terms of latencies or delays, throughput, as well as total energies. Next is about the simulation setup. The simulation setup is carried out under the random, shuffle, butterfly, and transpose traffics to test the performance of the investigated architectures in general. And the simulation conducted using the 64-core NOCs and 64-core WINOX. And in order to achieve a steady state, each simulation in the experiments was run for 100,000 cycles. These figures illustrate the traffic distribution patterns in 8x8 mesh topologies for random, shuffle, butterfly, and transpose traffics. Now, let's look into the result and analysis for this work. These figures demonstrate the result obtained when the average latency is plotted versus packet injection rate or PIRs. And the transmission latency is the time tackles, which is in cycles, for the packets to reach its destinations from its source. Overall, when it comes to traffic distributions, the WAN architectures shows a better performance in terms of achieving a higher PIR as compared with NOC, except in the case of butterfly traffics. However, for that butterfly traffic situations, although Winoc and NOC reach at the same PIR, which is at 0.014, the Winoc has a faster response time, which only taking 67 cycle as compared with 95 cycles that needed in NOCs. Uh, Also, it is interesting to note that in the case of transpose traffics, the WAN architectures give a significant increase of PIR, which is reaching of 0.15, whereas the NOC architectures only achieve 0.008. This graph shows the performance impact on the throughput, where the rate at which data packets can be transmitted by the infrastructure can be defined as the throughput. Moreover, the saturation throughput is the term used to describe the point at which the network demand reach its peak levels and the throughput is aligned with the workload demands. And once the network reach its saturation point, the system become incapable of effectively transmitting the generated data packets. The experimental findings indicate that the architectures of Winox consistently delivered a higher network throughput across the all investigated traffic scenarios. Specifically, it achieved network throughput at the rate of 9.18 for random traffics, 6.62 for shuffle, 6.65 for butterflies, and 7.7 for transpose traffics. This figure shows the simulation result of the architectures in terms of energy consumptions. And energy consumption in the network systems refer to the amount of electrical powers that consumed by the various components and operation within the systems. This figure presents the effect of energy consumption for the investigated architectures. In terms of in terms of energy utilizations, it is evidence that the binary architectures shows an increase in consumptions primarily due to the incorporation of additional transceivers components within the binary frameworks. When the architecture operates at its peak PIR saturation loads, the energy consumption values as follows, which are 15.2 millijoule for random, 12.6 for shuffle, 12.9 millijoule for butterfly and 14.4 millijoule for transpose, respectively. In conclusions, the aim of these studies was to conduct a comprehensive evaluation of multi-cost system performance in the specific context of NOC as well as wine architectures. Whereas both of them are implemented within 64 cores mesh network. This evaluation was encompasses the analysis of their behaviors under varying synthetic traffics, including random shuffle, butterfly, and transpose traffic pattern conditions. The conclusion drawn from the simulation result is that the wine architectures can provide a better performance, which is characterized by the enhanced capabilities at the higher PIR saturation loads, improved network throughput, and minimize latencies. And nevertheless, it is also important to note that there are trade-off associated between Windows and NOC as it consumes a greater amount of energies due to the additional element of transceivers in Windows. For future research, the focus will be exploring on the impact of traffic pattern designed for application-specific benchmarks such as Splash2 and Parsec. These are the main references for this research, and these are the rest of it. So with that, thank you very much for listening.